In this example, I'm going to show you how to use heuristics and the easiness of separation using different temperature and pressure conditions to propose what type of sequence you can use for this three-component mixture. So remember, you have three components. That means that you need at least 2 units, and you can do a sequence of 2, right? 2 potential combinations of those 2 sequences. The larger the number of components in the mixture, the more sequences you're proposed. Another thing that you need to think of is that you need to consider how much of those components you have in the mixture, because if you have a really low concentration of one of the components, you can assume, right? You can make assumptions that they need to be validated later, but you can make assumptions that they are not important for the mixture property, right? So you can simplify your stream, but you have to justify why you're doing that. Anyways, so here you have these 3 components. I have asked you all the semester to keep track of the normal boiling point. Remember, the normal boiling point is at 1 atmosphere. Many students feel tempted to just do the separations at normal boiling points because it seems that you're going to be saving a lot of money. But the reality is that you may have a lot of penalties, right? Because now you may have the reboiler or the condenser having really high energy duties to be able to meet, right, the specifications of the column at normal pressure. So in this example, I'm keeping track of the boiling point of the pure components at different pressures. You can do this in HYSYS by just copying the stream and adding a pure component and then putting the vapor fraction to be 0 or 1, and you can assume a mass basis if you want to of 100 mole, and that will give you the resulting temperature, right, that will correspond to the boiling point at that particular pressure that you're specifying. In this example of vinyl chloride, we have the reactor coming at 2580 atm. That's the exit of the reactor. And then we have here some options, like milder options, 12 atmosphere and then 4.8 atmosphere. Remember that it's okay to have a pressure around 5 or more. Even for gases, sometimes 10 is justifiable. So you always have to go to the heuristics, right, of recommendations in terms of the operating pressure for processes. So the other thing that we keep track of is the critical constants. Remember that the critical constant is the temperature or pressure of a gas or a vapor is in its critical state. Basically, what it means is that above this temperature, a gas cannot be liquefied by pressure alone. This means that the concept of distillation columns or the separations that we're typically accustomed to in a process that are more feasible, they are not possible, right? So we are trying to avoid to operate under critical conditions as possible. So there's a couple of options, right? I say that you have 2 options that you can do arrangement of the 2 columns that you know that you need. This is why going through the criteria is important. It's giving you a perspective of how many options you can have. So the option 1 is operating the column at 1 atmosphere, which is the tendency for many of the students to do this. However, if you look at this particular example, at 1 atmosphere, the hydrochloric gas is very low. The temperature, the boiling point is very low. That means that if HCl, right, is going on the distillate because it's the light key and the heavy key is going to be cutting off in the vinyl chloride. If this is the case, that means that the reboiler on the top, when it sends back in the reflux, right? The condenser in the distillate stream, it has a reflux, so it's sent back to the column. That reflux, right, the condenser is gonna have a high energy requirement. You need a lot of energy to actually get the condenser to meet the boiling point, right? You need the same temperature to actually liquefy the HCl and send it back to the column. So it's going to be a big penalty. So it seems initially like a good idea because overall the column is being operated at 1 atmosphere, so you may be saving some money on the fixed capital investment. However, the cost of manufacturing, which is what you're going to be paying every year, will be drastically affected. The second option can be to operate the column at 26 atmospheres, which in this particular case, V2, which is coming out of the reactor, is already at that pressure. So that means that you're saving money because you're not lowering the pressure at 1 atmosphere. Remember here in the first option, you need to lower the pressure of that stream to 1 atmosphere. So you also have to decrease pressure at some point. So it's also cost associated, and the delta P is high, right, between 26 and 1 atmosphere. So the second option says, well, let me just keep it at 26 atmosphere. I'm not having any penalty on the cost, right, on decreasing the pressure. Here, right, the stream coming from the reactor is already at that pressure, which is a positive thing. At that pressure, the HCl boils at 0 degrees, then a less costly refrigeration could be used. Remember, comparing the condenser operating at minus 84.8 is completely different as operating that at 0 degrees. So the reflux is going to be, the condenser duty is going to be less than the 1 atmosphere condition. Also, the chloro boiling point is close to critical conditions, which is not favorable. So look at this. This is why we need to keep track of this. Notice here the boiling point of dichloro is 242 at 26, which is really close to critical conditions. And remember, the system when you design it may be over specified or under specified. So you want to avoid, right, in case you have some sudden increase in temperature or pressure or changes, right, in the process, you want to avoid to meet the critical, have the critical conditions in the system. So, I mean, it has a pros, right? You don't need to lower the temperature. You're going to have less duty, but then you're going to have the problem with the operation, right? Because you're close to critical conditions for one of the components that has that is adjacent, right, to your desired product, which is the vinyl chloride. The third option is to operate the column at milder conditions. You know, the difference here is that the delta P between the inlet and the operating pressure will be less than decreasing that to 1 atmosphere. So at this pressure, the HCl boils at minus 26.2. The bottom product will have vinyl chloride and dichloroethane with traces of HCl. This bottom mixture will have a bubble point that can be calculated by HYSYS. You can actually take the stream coming down and at the same thing, right? You can actually specify the vapor fraction, depending if you have a dew point or bubble point. And you can put the operating pressure, and that will tell you, right, the temperature of the reboiler. At this temperature and pressure, it is far away from critical conditions. So we're, in this particular case, right, all of them, they're far away. If you consider just the mixture, which is the dichloro and the vinyl chloride, and you calculate that boiling point is going to be 93. So also the conditions are far away from critical. At this condition, low pressure steam is also adequate for the reboiler. So we are saving some money. We don't need high pressure steam to meet the 93 degrees. The condenser will still need to get to 26.2 to actually condense down the HCl. However, it's a big difference from 84 to 26. So, I mean, with this, we kind of decide, right, the operating conditions. So we can say that from all of the options, option 3 seems to be the most manageable between the two options. Notice that all of the options have pros and cons. You just need to decide and justify which one is the best. In this particular case, this design is taking into consideration your concepts of how the distillation column works, how it's going to impact the utilities on all that. So now for the second column, that is going to be dealing with the separation of our desired product, which is the vinyl chloride from the dichloros. So based on the boiling points, we should have the vinyl chloride in the likey and the distillates, right, and the dichloro in the bottoms. So here, what you can do, right, is you already separated the HCl, so you can just look at milder conditions. You can separate at 4.6 atmospheres. Distillate is nearly pure vinyl chloride and boils at 33 degrees. You can use cooling water in the condenser, which is available at 25C, which is a pros. The bottom's product boils at 146, and here what you can do is just use medium steam. Remember that the temperature of the bottoms affect directly the heat necessary for the reboiler. The temperature of the Leike directly affects the operating temperature also for the condenser. So this is why we're playing with different pressure conditions. Here, because we don't have any HCl, the condenser, as you can see, is 33.1 like I mentioned. And this is where I said that you can use cooling water, right, to do that. So at this pressure is good enough. It's not 1 atm, however, it's mild enough that the second column, C2, it should be C2 here, C2 will be operating at, recommended pressure conditions for a vessel, right? So it's not going to have an impact on the thickness of the investment, right, of the fixed capital investment for that column, because the thickness is not require any special materials or any special treatment. So with this, I'm showing you how to use all of the data table and all of the information that you have. Remember that this information you can also complement by calculations using HYSYS after you validated all of your activity coefficient. Remember, we are calculating boiling points for mixtures of components, like I did here for BC1, right? It has a mixture of dichloro and the vinyl chloride. You need to have the activity coefficients validated because those calculations depend on the interactions of the components, right, in the mixture.